Hello, my name is Marwa AlAlawi, and I'm a PhD student at MIT CSAIL working with Professor Stefanie Mueller. I'm very excited to talk to you today about MechSense, the design and fabrication pipeline for integrating rotary encoders into 3D printed mechanisms. This work has been done in collaboration with my colleagues from MIT CSAIL and collaborators from Accenture Labs. So MechSense is a method that uses multi-material 3D printing with conductive filament to augment 3D printed rotational mechanisms with sensing capabilities all in one pass. MechSense objects use capacitive sensing to detect speed of rotation, such as what this fishing rod game controller does, the angular position of gearboxes, and direction of rotation of measurement wheels. MechSense encoders can also be embedded in everyday objects to adapt to a user's needs. The smart desk lamp, for example, consists of two linkages and a middle rotational joint 3D printed with a MechSense encoder. As the user moves the lamp closer to the table to look at the textbook, the lamp's brightness increases. The reason we're particularly interested in augmenting mechanisms with sensing to make them interactive is due to recent advances in 3D printing. Over the last decade, 3D printing has enabled increasingly complex objects, including those with mechanical elements, to be fabricated. Traditionally, external sensors, such as off-the-shelf encoders, are used, but embedding them requires adjustments to an object's design as well as additional assembly. With conductive filament multi-material 3D printing, integrating sensors with 3D prints has become easier. For instance, researchers have shown how to print capacitive sensors for touch sensing and deformation shear cell sensors with 3D printed metamaterials. For rotational mechanisms, researchers have looked into using metal casting and copper plates to fabricate rotary sensors. However, the proposed sensor geometries either cannot be 3D printed in one pass or require manual assembly. Each rotating mechanism generally consists of two elements: a rotor, which is the moving part of the mechanism, and a stator, which is the stationary part. Since the rotor rotates freely about the stator, the sensing method between them must be non-contact based. Additionally, there should be no wires connected to the rotor to avoid entanglement. Hence, MechSense encoders use capacitive sensing, a non-contact based sensing mode, do not include additional components to be embedded into the 3D mechanism after printing, and can be integrated into complex internal geometries. So let's take a close look at what the sensor layout for MechSense encoders is. MechSense consists of a floating capacitor embedded into the rotating component, such as this gear. The floating capacitor is neither wired nor connected to the ground, and three sensor patches arranged in a circle around the static component. The sensor patches on the static part of the mechanism are connected to a capacitive sensing board. Here, we use an FDC2214 CapSense board, which uses an RLC circuit and can detect capacitances as small as 1 picofarads. When the floating capacitor rotates, it creates a coupled capacitance system between neighboring sensing patches. The amount of overlap between the floating capacitor and the sensor patches impacts the capacitance of the system. Getting the signal profile from each patch collectively allows us to determine the location of the floating capacitor. Let's take a closer look at the signal profile. In one rotation, we see 4 different features in the signal: a global minimum, 2 maxima, and a local minimum. The global minimum occurs when the floating capacitor is completely away from the active electrode patch, which we're examining the signal profile from. As the floating capacitor rotates and evenly overlaps with the current active sensor patch and the neighboring patch, a maxima is observed. Since the neighboring patches are connected through connection to the same sensing board, the coupled capacitance of the system is maximum in these positions. When the floating capacitor and active sensor completely overlap, we observe a local minimum. This is because the floating capacitor has no overlap with neighboring patches, but is still in close proximity to them, leading to small coupled capacitance. Finally, we observe another maximum at half overlap. we process the signal to find a characteristic equation relating the capacitance of the signal to the angular position. We collect data on our experimental setup, which we introduced in the technical evaluation. We collect capacitive signal data from the sensing board and angular position data from the encoder, which we regard as ground truth. First, we detect the extrema in the signal. Next, we divide our signal data into 5 segments based on these extrema positions, with each segment spanning 60 degrees. We normalize the data for each segment, which means that the maximum takes a value of 1, the minimum takes a value of 0, and anything in between is scaled by that. We then fit our normalized data to several approximation polynomials and Fourier fit functions. We found that a 4th-degree polynomial showed the least amount of error. For any incoming data, we use the same approach where we normalize the extrema values and fit the 4th-degree polynomial to each segment. We can also get the angular speed by tracking the timestamp and change in angles, and direction of rotation by tracking the sequence of extrema. Our MechSense sensing tool performs these same computational steps to retrieve angular position, speed, and direction of rotation. It does, however, require a calibration step prior to that, which helps determine what the baseline of the extrema values are and the starting position of the floating capacitor. We also built a SolidWorks plugin to make MechSense objects. We decided to use SolidWorks for 2 reasons. The first being a result of an exploratory survey with a hardware team at a consulting firm that showed that half of the respondents of the survey used SolidWorks as a design tool. The second being the prevalence of SolidWorks as a CADing tool in both academia and industry. Now, let's make a MechSense wheel together. First, we launch the MechSense SolidWorks plugin and indicate that this object is the stationary part of the mechanism. We choose the center of rotation and surface to where we would like the encoder to be added to. The result is 3 sensor patches generated on the face. Next, we would like to route the sensor patches via traces where wires from the sensing board could be connected to. We create a 3D sketch in SolidWorks and use the trace generation tool to generate a sweep pattern. Next, we generate the floating capacitor via a single patch on the rotating part of the mechanism. We're ready to 3D print. We use a dual extrusion Ultimaker S5 printer with an abrasion-resistant CC print core for the conductive filaments. We use PLA for the non-conductive regions and multi-3D electrify filaments for the conductive parts. As you can see, MechSense objects are printed in one pass. The only wiring necessary is to connect the stationary patches to the capacitive sensing board, which we do so by pressing wires to the conductive filament using a soldering iron. Now, we move to the technical evaluation. Our technical evaluation setup consists of removable MechSense stator plates and floating MechSense capacitors, i.e. rotors. These rotors are attached via shaft to a stepper motor with an encoder embedded within it. For all of the evaluations, we used the same environment and rotated the gears at 10 RPM for 50 rotations. For the gear we used to derive the characteristic equation from, we get a median value of 1.4 degree error in our angle estimation, with max error being around 7 degrees on average. We then test MechSense further. We evaluated the effect of separation distance between neighboring electrodes, which we refer to as PLA separation distance. We noticed that as the PLA distance increases, the number of outliers in angular position estimation error also increases. This is because the shape of the signal changes as the separation distance increases, where the slope leading to the extrema becomes less steep. Next, we evaluated the effect of reducing the area of the patches to 60% and 20% of the original patch size. We found that the decrease in patch size generated more outlying error. This is due to decrease in peak-to-peak distance, which makes the signal more susceptible to picking up noise from the environment. Finally, we evaluated hand proximity at 50 centimeters, 20, 10, 5, and direct touch. Since we cannot touch the rotating floating capacitor, direct touch was performed by touching the MechSense stationary plate. For the duration of the rotations, the user's hand was kept at a constant distance using an armrest. As we see here, up to a distance of 20 centimeters, there is minimal effect of hand proximity on the signal. However, as that distance decreases, the higher the error becomes. This is because when a user's hand becomes closer to a MechSense encoder, the hand interferes with the capacitance of the signal and overall shifts the position of the extrema. So what can MechSense be used for? It can be used as a game controller that measures a user's manual rotation and input. In this game, the user rotates the fishing rod controller and catches a fish. It can be used on a gearbox to measure the position, velocity, and direction of rotation. It can be integrated in everyday objects like a desk lamp. And finally, as a measurement wheel, where angular position is mapped to distance, and forward motion adds length, while backward motion subtracts length. With MechSense, we investigated how to integrate sensing into rotating mechanisms via conductive multi-material 3D printing. For future work, we plan to explore how to increase the robustness of our sensing method to external noise and develop 3D printable sensors that can extend to other mechanisms.